Hello, my name is Nomin. I am an undergrad researcher working with Dr. Ning Wu and Ashraf Haq to create a novel approach to propel micromotors using a combination of magnetic and electric fields. Colloids are particles on the micro to nano scale that can be applied to a broad range of areas in biomedical applications. Now, when there's an object that small operating at a low Reynolds number, there becomes a need for continuous power supply that creates challenges in locomotion mode and control. There are a couple ways to power micro-robots, such as self-propulsion using chemical reactions and external propulsion, which uses electric fields, light, or acoustic waves. In this research, we have developed a combined actuation method to control locomotion and navigation of colloids using both magnetic and electric fields. In our experimental setup, we used around 5 to 10 microliters of dyno beads suspended in room temperature deionized water. This suspension was sandwiched between two indium tin oxide glass electrodes shown in figure 2. This whole electrode slide system is then placed inside a magnetic apparatus which contains 5 air-cored copper solenoid coils. Using MATLAB and the generators, we were able to apply and control DC electric field and AC magnetic field currents to our electrode system. With our apparatus, we are able to create chains of beads and tilt them to our desired angle. This video shows a chain of 21 beads tilting due to a DC magnetic field. In order to make vertical chains of colloids, the magnetic field aligns the beads in the XY plane and the length is measured by pixels represented by the schematic. Then when the magnetic Z field is applied, the chain elevates from the XY plane at a certain angle. To calculate this angle, the length of the chain projection is measured, shown in yellow, using simple trigonometry. Tilting alone due to the magnetic field did not propel the chains into motion, but it was found that the addition of an electric field induces angular reorientation and movement. Here is a video of a couple of chains of colloids moving at an average velocity of 0.33 micrometers per second due to an electric field of 1300 Hz and 7 volts. Previously, such geometry was found to move only when they are forced to locomote by continuous change of direction of applied electric field. However, now we can demonstrate this reversible geometry of asymmetric tilt can be propelled by a field that is changing with time. As seen in figure 4, we can even optimize velocity depending on the chain angle. Furthermore, as seen in the parity plot, the chain angle measured from the projection length is not exactly equal to the field angle calculated from the YZ magnetic currents. Due to the additional electric field, it seems to cause a shift down or a decrease in the chain angle. With this in mind, we can tune the chain angle to obtain a certain velocity only by changing the magnetic field conditions. In the end, we can conclude that first, the locomotion of tilted chains is solely activated by DC electric field. Second, the direction acquired by the magnetic field is maintained in such a manner that the DC field-induced flow cannot alter the directionality. Third, micromotors can attain an optimal velocity corresponding to certain tilting angles. And last, we can conclude that combining electrokinetics and magnetodynamics, we can more effectively control and move colloidal products into things such as braking and steering without emphasizing on initial design. I would like to acknowledge and thank Dr. Wu and Ashraf for the continued support and guidance. I also could not have done it without everyone in Dr. Wu's lab. Thank you!